looks good.
Yeah?
Yeah.
Okay. Let's see if I have a video here, if it works well.
Yeah.
Do you see the video?
Yeah.
Okay.
Yes, yes. Is there any sound?
No, it's without sound.
Yeah, that's beautiful. That's nice.
Okay, very well. Then that's it. I think should be fine.
Yeah, everything's good. Okay, we still have more than 12 minutes. So I just grab my coffee.
All right. And that's
Elda, are you ready?
yeah, I'm ready.
Okay, cool, good. Hello, good morning, good afternoon, and good evening. This is Paul Liu from NC State University. Welcome again to the World River and Delta System Source to Sink webinar series. And today we are very happy to invite Professor Elda Miramontes from University of Bremen, Germany, come here talk about mixed turbidite-contourite system. How can ocean currents affect the transfer of sediment to the deep sea? And as always, before I introduce Elda, I want to mention more about this talk series. So as always, this talk series, all the previous talk have already been archived on our YouTube channel, and you can go there to take advantage to use those presentation for your research, for your research, for your education, for your group discussion. And at the same time, we also have a Twitter account, Source to Sink. We will announce all the talks and all some related Source to Sink River Delta news. You're welcome to follow us. And next week, we have Sophie Hager from Ephemeral, France, come here talk about the organic carbon from source to sink in a built inlet. So the time is interesting because this coming weekend, Europe will change from day saving time to a standard time. I'm not 100% sure. I think, only this coming talk, next week talk, because United States summer saving time is November 7th, ended November 7th. That's very strange. So we still keep a US Eastern time 9 a.m. I guess London will be 3 p.m. Paris will 4 p.m. I'm not sure. Oh, maybe I need double check. We need double check. So just I will keep you informed, update about the time by email and Twitter, okay? But just next week, Sophia will come here talk about organic carbon. And Elda, as I mentioned, now is an assistant professor at Center for Marine Environmental Science, University of Bremen, Germany. And before that, she also was a postdoc at Ephemeral here, also University of Western Brittany and Ephemeral. So Ephemeral is a great institute. 20 years ago, 2001, I visited there for 1 month. And so also Elda got her PhD from there, as you can see, and originally master degree from Spain, University of Vigo, yeah. So her research, I begin to know her by her recent wonderful publication about internal wave, how the sediment, particularly in Madagascar, in Africa, east coast of Africa, how the sediment on the shelf and the slope transported by the ocean current. As you can see, her research interesting mainly it's the sedimentary process and the control seafloor morphology and the sediment distribution into the deep sea. So use the geophysical data, multi-beam, seismic, sediment core, and on-site measurement. So I think now, Elda, we are looking forward to your talk. Please share screen.
Yeah, thank you very much for the introduction. Let's go.
Yeah, looks good.
Okay, very good. Gonna take the laser pointer. Yeah, well, thanks, Paul, for the introduction. And it's great to see that there are so many participants already here online. And yeah, and I hope you enjoy this talk and that we will have a discussion afterwards. Yeah, so today, although this webinar series has the name of River and Coastal Delta Systems, today I'm gonna move a bit farther downslope. But in here you can see already in my first slide that yeah, I have a coastal system. This is the Po Delta, and this illustrates very well what we are trying to analyze also in the deep sea. So we can see already how the currents are deflecting the plume that is coming from the delta and is moving all the sediment only to one side. Could be great to have something like that in the deep sea. I hope maybe with the future technological developments, we will be able to have such images, but so far we have to work with less nice data than people working on deltas. But I hope we are able to illustrate as well how this process and these morphologies are formed. So what I'm going to present today is a part of a study that was carried out in collaboration mainly with IFREMER, with the University of Utrecht, the Geological Survey of Canada, and the Royal Holloway University of London. And also we also have a Twitter account, myself and my group. So if you want to have a look at our recent studies, what we are doing, we often publish everything in our Twitter accounts. So just follow us. So I would like to start with the concept of a source-to-sink system. So of course, all the participants here are well aware of what it is, but I would like to point out some key ideas that that's also what motivates our study. So usually the common view of a source-to-sink system is in 2D, where we have a catchment on land, a zone where we have mainly erosion, and then we have a zone of sink that can be already on land on the coast, or finally also in deep water environments. And this is often seen as a whole system, so that it goes from the source to the sink, and that the sink is directly connected, or at least is not so far away from the source that is on the continent. So this doesn't take into account much of transfer along the slope or along the shore. Although it's well known that longshore currents can already deflect all the sediment that comes from the continent and can be finally deposited farther longshore, so farther in the downstream direction of these currents. So for example, this is very typical for the Po Delta, some deltas in Mediterranean, such as the Po Delta or the Nile Delta. You can see here the plume of sediment being deflected by the current. So for example, in the Nile Delta, we have also all these deposits that are being transported farther north later along the Levantine margin. And in the Po Delta, there is a huge accumulation all along the continent. So you can see here in the upper image, a satellite image where we see all this sediment in suspension here near the continent. Here is the Po Delta, and here there are many other rivers that also bring sediment to the sea. And these arrows show the main ocean currents in the area. And this here represents the sediment accumulation rates of sediment along the continent. And here, of course, they are the highest at the Po Delta, but you can see already that the position is very asymmetric. So it's mainly in the southern part of the delta because of these currents that are pushing the plume towards the south. But also we have all these deposits along the continent that is very asymmetric. So it's mainly also in the southward direction. And that has a maximum accumulation in the middle. So if we have a look at the cross section, it looks like that. So this subaqueous delta has on the top less accumulation, then in the center highest accumulation, and less again in the bottom. And the upper part is controlled because of waves and currents that are in shallow water depths, and that create high shear stress, bottom shear stress that inhibits sedimentation in this area. And then we have a minimum of energy in the middle, that is where there is the highest accumulation. And again, a higher energy in the lower part, already on the shelf, where bottom currents, so currents flowing near the seafloor that are related to the circulation, are also transporting away the sediments, and that's why we don't have any deposition in this area. So when we have a look at this sketch that was done by Claudio Pellegrini and modified from Romans, so we have the typical source-to-sink system that was already done by Romans et al., where we see this along shore transport on the slope. And we added also all these other features that can be formed on the shelf, but also on the slope and on the abyssal plane that are related to currents, so bottom currents flowing near the seafloor that follow the slope contours. That's why they are also often called contour currents. And these currents can generate particular deposits that are called contourite drifts, and we can find them at any water depth, so from the shelf edge down to the deeper part of the basin. So all these currents can transport and redistribute the sediment that is brought from the continent through different processes, and they can generate even in some parts where this transport is very effective, they can transport very far away these sediments, so they can disconnect the sink from the source. And during my talk, I'm going to focus on this part of the system that is deep water environments, everything that lies below the continental shelf. So in this type of environments, we usually have three main types of deposits. We can have pelagic or hemipelagic sedimentation that is formed mainly by vertical settling, so in a quiet environment without strong currents. But if we have an environment with a strong circulation, with strong currents near the seafloor, then this can control sedimentation and erosion and can form contourites. That it means contour is just any type of deposit that is affected or affected by bottom currents. And then we can also have turbidites or mass transport deposits, or gravity-driven deposits that are also very often found in this type of environments. And these turbidite currents, particularly, that are gravity-driven processes where the sediment is transported in suspension, they usually flow downslope along submarine channels, submarine canyons. So for example, here there is the case of the Congo Canyon in Western Africa. You can see here the general map by a paper from Spiro Zavala et al. And here the multi-bathymetry with the submarine channel. And in this case, they did some measurements in this area and they could measure the turbidity current itself. So you can see here the results. This is the velocity of the turbidity current that was flowing downslope along the canyon. And this process can be very energetic. So in this case, it reach 2 meters per second, can be sometimes even higher velocities and can last a relatively long time. In this case, was a very long turbidity current that lasted more than 5 days. And that's why most researchers assume that because these processes are so energetic and they are also usually confined into submarine canyons. Like here, you can see this turbidity current has a maximum height of 80 meters, but the canyon itself is much higher, above more than 200 meters of height. So the turbidity current is mainly confined within this canyon and also is mainly protected from the ambient currents. That's why it was assumed that this type of processes cannot really be affected by ocean currents because they are protected inside the canyons and also they are much more energetic. Usually their velocity has an order of magnitude higher, is an order of magnitude higher than the velocity of bottom currents that are usually below 20 centimeters per second. And very often turbidity currents can have velocities of more than 1 meter per second. But in the recent years, well, since quite many years already now, there has been more and more evidence that actually deposits formed by turbidity currents and also formed by bottom currents do interact, the deposits and probably the processes themselves, and create particular sedimentary deposits that are not exactly the same as the end members of a turbidite or a contourite. So we can have a mixture in between that is generated by this interaction of both gravity-driven processes, in this case mainly turbidity currents, and also bottom currents. And it has been suggested that there are 3 main types of mixed turbidite systems. So this mixed turbidite system, mixed turbidite-contourite system refers to this kind of systems, depositional systems, where we have both deposits or the interaction of bottom currents and turbidity currents. And we can have, well, I'm going to show you now some examples. We can have first a passive interaction, and this is when we have both sedimentary systems that happen in the same place, so we can find them in the same place, but they have more or less the typical characteristics of the end member. So we can identify pure contourites, we can identify pure turbidites, but they coexist. So here you have an example from northwest Spain, offshore Galicia, and you see here the continental slope. This is the continental shelf here, the slope. And at the foot of the slope, there is like an outcrop, kind of a seamount attached to the slope. And next to this seamount, there is a contourite drift, so a deposit formed by bottom currents. You can see it here more clearly. And a moat that is an incision generated by bottom currents. So the flow was the highest here inside the moat, and then there was the formation of this contourite drift next to it. But on the sides, we also have submarine channels, some gullies, and many turbidites all around. So we can find both types of deposits in the same place. In other areas, the interaction is stronger, and actually bottom currents affect the deposits formed by turbidites. So this is the case, for example, offshore Brazil, where they found phased interaction. That means phase that we have first one process is occurring and then next process is affecting the deposits left by the first process. So for example, we have here some submarine channels and lobes that were forming an interslope basin on the slope. And then we have here bottom currents that are very strong flowing at this level, and they were eroding the seafloor, forming these furrows that are incisions that are elongated in the direction of the current. And then even there were Balkan dunes that were formed at this location. And all this sand that was found on the slope, so they drill a well here. See here the result, and this level corresponds to a sandy deposit. So all this sand was brought by turbidite currents and was deposited there, and then it was later on reworked by bottom currents. Another example is from the Mozambique Channel. So this seismic profile here corresponds to the Zambezi Valley that brings a great part of sediment from the Zambezi, related to the Zambezi Delta. So here you can see the talweg of the valley that is mainly formed by turbidite currents, but all these flanks of the valley, they are strongly affected by bottom currents. So you can see here, this profile is located here in the bathymetry. We are at this location, and this is the backscatter from the bathymetry. So the flanks of the valley also have a high backscatter, so we have also sandy deposits on the flanks. And actually what's happening here is that the bottom currents are accelerated along the flanks of the Zambezi Valley, and these bottom currents are eroding the Zambezi Valley. So we don't have any turbidite deposits on the flanks. There is no overspill, there is no formation of levees, and all these flanks are eroded by bottom currents. And we had to course on both sides of the flanks, and we found that at the surface of the course, we find contouritic sand that is mainly formed by foraminifera. So we have pelagic sediments that are being winnowed by bottom currents, and then only the coarser part that corresponds to the foraminifera in this case remains there, and most of the fine material is winnowed by bottom currents. And then we have the case of the synchronous interaction, and in this case both processes are active at the same time, and they interact with each other and form a particular morphology. And this has been suggested to be the case for some unidirectionally migrating channels in the South China Sea, and also from some other asymmetric channels in the Congo Basin. And in this case, some authors, including Gonetal and others, have interpreted that these channels migrate in the direction of the bottom currents, so that we have a transport of sediment in the direction of the bottom current, in the direction of the bottom current that is deposited in this side of the channel, and then with time the channel migrates in this direction. Then other authors suggest that the synchronous interaction can actually lead to a different deposit, where the shape is similar, but the process will be different. So Shamugan, for example, already suggested in the 90s that ocean currents could deflect the upper part of turbidite currents and transport this sediment, this plume of sediment to the side, a long slope. And also it has been suggested for Tanzania and northern Mozambique that some very asymmetric submarine channels were formed by this deflection of the turbidite current generated by bottom currents, and that in this case the conceptual model would be that the channels are migrating in the opposite direction of the bottom currents. So here you see another example of the seismic from the Mozambique margin, from the northern Mozambique margin, where you can find these asymmetric channels with a more developed levee on one side and this migration in the opposite direction. And Furman et al. Published some measurements of bottom currents in this area with some moorings in the upper slope. So the same here, the same submarine channels that are asymmetric and have the actually, of course, they have the main levee that is being formed in the downstream direction of the bottom current. So it would be in this case that we have the main development downstream the bottom current. So at the end, there is still some discussion of the different types of deposits that we can find within these asymmetric channels, and also these channels that are migrating in a particular direction. And the interpretation of the bottom current that will generate this type of deposits is opposite. So in one case, we have bottom currents that are bringing the sediment into the channel, and we have the final migration of the channel in the direction of the bottom current. And then there is the opposite conceptual model, where we will have the bottom current in one direction, and the deposit will be on the other side of the channel of the levee, and the migration of this channel will be in the opposite direction of the bottom current. So this is important to decide when each interpretation applies, or if it is physically possible to have this kind of process in nature, because we could use this type of deposit to reconstruct paleo circulation. So we need to really better understand how these processes occur, how this interaction occurs, but also not only to reconstruct the direction of the currents, but also to understand how the particles are being transported. Because now with the sediment, we don't only have clay, sand, silt, but we also have organic carbon. We have nowadays also microplastics. So it's important to understand for the whole scientific knowledge. So also for implications for ecology, for pollution, and for climate, how these particles are being transported, in which direction are they mainly going to go on, and to be retransported all along the slope, or are they going to remain close to the channel or inside the channel? So this is very important also for hydrocarbon exploration, for instance. So that's what all why we were interested in this topic, and we decided that we would like to do some experiments to try to better understand how this interaction between turbidity currents and contour currents, so bottom currents flowing along slope, how this occurs. So we did that at the University of Utrecht in the Eurotank. That is a facility led by Joris Echenhausen. So we were doing that in close work with him and his colleagues. And we were also doing that mainly together with Ricardo Silva Jacinto from IFREMER and Giovanni Ponetti, a master student at that time that was visiting Utrecht. So the tank looks like that. It's 11 meters long and 6 meters wide. We created a slope on one side of the tank with a slope of 11 degrees. And we performed a submarine channel on the slope. And then we generated a circulation inside the tank with some pumps. So here you have, there's when we were preparing the floor of the tank so that it's all nicely flat. Then here already filled with the sediment with the channel in the middle, and here's the slope. And this is the pump system we built to create the circulation. So we had 3 pumps that were pushing the sediment on one direction, and we're creating a very homogeneous current vertical. So at the end, we had here along the slope currents that were flowing also along slope and that were going to interact with the turbidity currents that would flow here downslope. We measured the velocity inside the channel here with a velocimeter that measures in 3 directions the velocity. It looks like that. So it was located in the middle of the channel. Then we did 4 experiments. One where we did a turbidity current without a contour current so that we could compare with the reference where we don't have contour currents. Then we did 3 cases of contour current. That one that had an average velocity of 10 centimeters per second at the location of the channel, one 14, and a third one 19. You can see here the results of the measurements of the current for the 3 different experiments. And one is the downslope component, and the other one is the along slope component. So you can see the downslope component is very weak, almost nothing, because it's oriented along slope. And then we have a quite homogeneous velocity vertically in the top. The configuration that we use for the turbidity current was based already in previous studies. So the group of the University of Utrecht has a very large experience working on submarine channels and turbidite systems from an experimental point of view. So we mainly use their configuration that we knew that was working very well to create summer channel levee systems and submarine lobes. And we followed that. We chose one configuration that was the one of the studies from De Leeuw et al., where they had a nice development of levees and also overspill, because it's the one that we thought would have highest interaction with the contour currents. And so this channel was 80 centimeters wide and 3 centimeters deep. And then we used always the same mixture of sediments in the mixing tank to create the turbidity current. So all these factors were kept, these parameters were kept constant, and we only changed for the different experiments the velocity of the contour current. And here you have a video with 2 of the experiments. On the top, there is the turbidity current without contour current, and the bottom is the turbidity current with contour current of 14 centimeters per second. That was the moderate contour current that we modeled. And you can see that in this case, in the upper part, there is a symmetric overspill. Let's put it again. There is a symmetric overspill. So we have the turbidity current coming down, and then the turbidity current is quite symmetric on both sides. But from the beginning already, we see that part of the sediment suspension is taken by the contour currents in the other case. And the whole turbidity current is being affected by this contour current. So not only the upper part, as suggested before, but the whole turbidity current is being pushed to the side by the contour currents. And we have the development here of a front on one side, where we have the contour current that is blocking the overspill, and then this generates at the end that we don't have any overspill on this side. So here the snapshot at the end, we have without contour current a symmetric turbidity current, but with the contour current, we have already strong asymmetry in the turbidity current. We see the sediment suspension being affected by the contour current, and also a lateral front that forms on the side of the contour current. And here are the results of the measurements, of the velocity measurements. So these visual changes that we see from the videos are also very clearly observed in the velocity measurements. In this first graph, you can see the downslope velocity. So in orange is the case without the contour current. And then when we increase the contour current from 10 to 14 centimeters per second, we see an increase of the maximum velocity of the turbidity current. But when we increase even more, actually the average maximum velocity decreases. And that's something we still don't fully understand. So we don't know if this is always the case or if it was only in these 4 experiments that we did. So we are currently starting a new project. So a new PhD student is going to start right now in Utrecht to keep working in this topic. So hopefully in the coming months, we will have more information about why these kind of things actually happen. And yeah, so here you have the main velocity of the contour current is around here, much less than the maximum velocity of the turbidite current that we find. But we do see that the turbidite current has a very big change in the along slope velocity with the contour current. So in orange, you can see without the contour current. So it's mainly close to 0, the along slope velocity, because the whole turbidite current goes mainly downslope. But when we start increasing 10, 14, 19 centimeters per second, we see that from the beginning, the whole turbidite current is turning a long slope and is progressively turning a long slope until the upper part is already allineated with the contour current. And we see that very well when in the plot of the direction. So if we have 0 is downslope, and then in this case 90 will be a long slope. And in this case, you see how very soon the current starts to turn, and then the upper part is already completely allineated. So we have a kind of a spiral structure. The whole turbidite current is turning. It's not just the upper part, it is deflected. So the whole turbidite current is turning. And this starts to happen especially above the submarine channel. So inside the submarine channel, it's mainly confined, and this deflection is not so important, but above it, we have a strong deflection of the turbidite current in the downstream direction of the contour current. So we also observe these differences in the deposits that are left behind by the turbidite current. So we have here the deposition that was that happened during the 4 experiments. The first one is without contour current. The second one is with 10 centimeters per second, then 14 centimeters per second, and 19 centimeters per second. And then here below, you can see the cross sections at this location, before in the red, the black line, and after the experiments, the red lines. So without the contour currents, we have mainly the formation of symmetric levees. So we have on both sides levees that are being formed, and also you can see some bed forms that are both sides, more or less the same size on both sides. But when we start increasing the contour current, we start seeing that one levee develops less and less, and even here almost completely disappears. And also the bed forms kind of disappear from the side that is upstream the contour current, where we saw this lateral front in the videos. So here in the moderate velocity, we almost don't have any bed forms, and then the field of bed forms becomes also bigger on the side downstream the contour current, and also the deposit of the levee seems to be a bit larger. And with the stronger velocities, we almost don't have any levee on this side. It's very narrow, and probably this will be unstable and will disappear after a second event. So these kind of deposits are very similar to the ones we observe in nature. So you have here an example from the Atlantic Ocean offshore Canada. And here there are some submarine channels with some levees on both sides. And here you have the cross section where you can see that there is one levee much more developed than the other one. And also in the bathymetry, we recognize that the bed forms, in this case the sediment waves, are only located in the downstream direction of the contour current that in this case flows mainly towards the south. southwest. And yeah, so we have exactly the same asymmetric levees with a larger levee that is downstream the contour current, and also more bed forms in this side. So if we were also wondering how okay, the morphology seems to fit, but how possible it is that this really happens in nature. Is it realistic, the proportions we did of the turbidite currents and the velocity of the contour currents? And we think that, yeah, they are very realistic. So in our experiments, the velocity of the contour current was between 10 and 25% of the maximum velocity of the turbidite current. So these are values that could be reasonable for natural environments. So for example, if we have a contour current of 20 centimeters per second, the weak interaction would correspond to a turbidite current of 2 meters per second, which are values very common in nature. And also we could have a strong interaction at this velocity with turbidite currents that are less than 1 meter per second. And actually that's also very common, and probably most of the turbidite currents are not the strongest ones, but we also have many events that might be a bit weaker. And this is an example here from the Mediterranean Sea, from the Var Canyon. And here you see the horizontal extension and then the velocity. And the velocity has a maximum of 60 centimeters per second near the seafloor, but also the upper part is much weaker. So this is going to be the part that is going to interact mostly with the turbidite current. So we can imagine that these kind of turbidite currents could be easily affected by contour currents. So of course, this depends on the environment. It's not going to be that contour currents can affect turbidite currents and submarine channels everywhere in the oceans, but there can be many environments where this interaction can happen, and therefore the transport downslope can be affected, could be deflected along slope, and we could also have an effect on the morphology that is left behind. So to conclude, this was a preliminary study. So it was the first time that this kind of experiments were done. So we know that we don't have all the answers to understand how these processes interact. So it was just a begin to prove that this is possible, and that we need much more work and many new studies dealing with all types of analysis of more experiments, modeling, numerical modeling, but also measurements, direct measurements of these currents, and analysis of cores and seismic to really understand how the system works. But some of the main questions that remain to be answered are, for example, how is the temporal spatial interaction of these flows? As I said, this probably doesn't happen everywhere. In which kind of environments do we find it? Because often it's also difficult to differentiate only from the deposits how the interaction happened. If it was really synchronous as we model here, or if it was a later deposit that was formed. So for example, we had first the turbidite, and then it was eroded on one side, but later on by bottom currents, and maybe that would be rather a phase interaction. So all these interactions need to be better understood. And also, what are the characteristics of bottom currents? Because now what we analyze are contour currents, so bottom currents flowing along slope, but there are many other oceanographic processes that could also affect the transfer of sediment from the continent or from the shelf to deep water environments. For example, it's known that internal tides and internal waves are very strong, especially in submarine channels and submarine canyons, and they can even affect the turbidite current while it is flowing. They can also resuspend sediment inside the submarine channels. So these are also other processes that have a different direction. In this case, is upslope and downslope, and we still also need to address this and better understand how they may affect sedimentation within channels and canyons. Then another factor that strongly affects this interaction is the structure of the turbidite current. So it's not the same very dense turbidite current that is quite shallow and flows mainly near the seafloor and doesn't overspill much. Because in this case, of course, if it is very fast and doesn't overspill much, the interaction with the currents is going to be weaker. But if we have another type of turbidite current that has a lower concentration and is very high and much higher than the channel, then the interaction could be, of course, stronger. So it depends on the turbidite current, on the degree of confinement, of course, that goes together. But also within one system, probably the type of interaction is not going to be the same in the upper part of the canyon, where the canyon is very deep and deeply incised. So the turbidite current is going to be protected from the main current flowing along slope than in the lower part of the slope, where we have already the formation of channel levee systems. The channels are smaller and less deep, so the turbidite current can overspill more and also have a stronger interaction with the circulation. And then a big question always is what is really creating the asymmetry in the deposits we observe in nature? Is it always because of the contour current pushing the sediment to the side, or is it only because of the Coriolis force acting on the turbidite current itself, and that generates also a deflection that with the distance and time, the turbidite current is going to move to one side. So to the right in the northern hemisphere and to the left in the southern hemisphere. So this is also a critical question that is at present still difficult to address. So I hope that yeah, with this question, we can also open the discussion and motivate future work to bring this topic a bit forward, and so that we better understand how ocean currents actually affect this transfer of sediment to the deep sea. Yeah, that's all for me today. Thank you very much. And looking forward to the discussion.
Wonderful. Fantastic, Elda. That's a great talk. So let's see. If you have any question, please unmute yourself. Go ahead.
Yeah, Paul.
Yeah, Jingting, go ahead.
Hi, Professor Miramontes. Very good talk. I have a few comments and small questions. You know, I really have been susceptible on this interaction between turbidity current and contour current. In my mind, because you know, as you mentioned in the beginning of the talk, the magnitude of the two current almost always one or two order of magnitude different. But after seeing your experiment, now I think you might have changed my mind a little bit. Thank you. That's very good work.
Thank you.
You mentioned in the last point of your conclusion, the Coriolis, on the map of Canadian shelf, you know, the asymmetry of levees. Many years ago, Bill Normark and Tony Boeing published a paper on that. They argued that in the northern hemisphere, because of Coriolis force, you always see the asymmetric levee on, you know, one side or another, depending on which way the turbidity current goes. So Yeah, I would be careful in relating that asymmetry to the contour current. One question is, you have a very good start, but the experiment used a very shallow channel, and to me it's relatively too high contour flow, the contour current. You use the 10 centimeter per second or something. In my observation over the years, the contour current I have been seeing is almost always less than 10, but that doesn't mean you don't have over 10. So do you have a plan of doing a series of experiments using the ratio of contour current to the turbidity current as a guide? You know, you from 0.1 to 0.01, whatever, to do a series experiment, and finally you get some kind of relationship or some controlling formula on that. Thank you. Very, very good work.
Thank you very much. So it's a great comments, and I completely agree with all of them. If we start, for example, with the part of the Coriolis force, so the same way that it's difficult to prove that it's because of contour currents is the same as we have when we argue that it's because of Coriolis force. So we will need to really measure directly what's going on there to know what might be the most important factor, and maybe it's both of them. So that's something that I don't exclude. So I'm not against the interpretation that the Coriolis force in the northern hemisphere generates at the end asymmetric channels. But yeah, but what we try to demonstrate here is that the contour currents can also do it. Then when, why, that's still not so clear. And yeah, according answering to the question about the future plans, there is this new project in the University of Utrecht in which I am also involved. And this PhD student is going to do different settings. Also, we are going to change the shape of the channel to, as you say, to check what's the effect of the channel, and also change the velocity and try to do also more measurements of the velocity. So we will try to test a broader range of parameters so that we better know what's going on. This one, we try to keep it simple and just change the velocity to actually know if this was possible or not. That was our main objective. And then now that we know that it's possible, we can start trying to answer more detailed questions about the process itself, how it happens. And then if 10 centimeters per second is a lot or not, it depends, of course, in the area, but there are also many areas in the world where we could have this kind of velocities quite often. But yeah, it will be also interesting to test a bit weaker currents. And as you say, probably in this case with experiments, the best could be to work with this ratio so that we can transfer it more easily to the nature. I'm not sure if calibrating will be possible, because also the type of sediment we are using in the experiment is, of course, never the same as we can find in the nature, and probably the amount of clay you have in there and many other factors can also strongly affect. So I think we are still a bit far from the possibility of calibrating, but at least to know how each parameter may affect the end result would be already very valuable information.
Nicely done. Keep us posted if you do have new result.
Yeah, thank you.
Okay, cool. Next is Davidretta. You have a question?
Yes, hi, Dr. Miramontes. Thank you. It was a great talk, and I'm actually interested in the question whether carbonate particles can also be transported by contour currents specifically. And in your talk, you mentioned that in one of the slopes, you found that there was a lot of forams because the idea is that the finer particles were winnowed by the contour currents and the forams were left behind. So my question basically is that like most of the experiments and most of the studies consider only the sort of the siliciclastic particles, and why the carbonate particles and the biogenic carbonates are not considered. Uh, and secondly, like, do you think that the particles can be transported for longer distances? Because in some parts of the world, the contour currents themselves can have like several tens of centimeters velocities, especially during some episodes when the velocity goes up. So do you think that during these episodes, both the siliciclastic and the carbonate particles, including foraminifera, can be transported for long distances?
Yeah, I definitely think that carbonate systems can also have this kind of interaction. Actually, I was working in the Mozambique channel in the last years, and we also found some asymmetric channels related to some carbonate platforms. So it was an asymmetric levee, and these levees were also strongly affected by contour currents. So we found some scours and contourite drifts that were formed by this carbonate deposit. So yeah, around Bahamas, Maldives, all these large carbonate systems, there are a lot of deposits formed by contour currents. So I'm quite sure that the gravity-driven processes that are found in this area are also in part at least affected by these contour currents. And then how exactly this is happening is always more tricky to do experiments with carbonate sediments, especially to get the real sediment. Because of the shape, the type of material you have, you cannot just buy it that easily. With the sand is very easy, you can buy normal sand, and that's why siliciclastic experiments are much more common than the experiments with carbonates. But there are some people also in the University of Utrecht and in other, I think in Saudi Arabia, some groups there were also studying carbonate systems, and so turbidite currents are formed with carbonate sediment. And yeah, so it is possible. It's just more difficult. And yeah, so I guess if somebody has interest, this can be done. So there's nothing against it. And of course, the behavior of these particles is going to be different, and probably the final deposit is also going to be different. So especially forams, they can float more and they can probably be transported much farther away. This is also well known for the pelagic sediments, that actually the forams are not usually deposited right where they died. And there have been some studies where they analyze how they are transported and where they finally end up. And in some places of the world, this can be very far away. So especially, for example, in the Mozambique channel, you can have some forams that were living in northern part of Mozambique, and then when they die, they are deposited in southern part of South Africa. So when you start having a look at maybe try to reconstruct from these forams temperature and other parameters, of course, it's not going to be the same almost in a tropical place, and where it's finally deposited was already almost a polar environment. So yeah, this can be actually possible in carbonate environment.
Good. Elda, we have
Thank you.
three. Yeah, Elda, we have three more questions. One
Okay.
is Li Shuan Li. Go ahead.
Okay, thank you very much for your excellent talk. This is Shun Li from Beijing, and I have a small question. I found in your experiments, there is a very interesting thing is that the depositional thickness in your channel, the upstream is thicker than the down, or not the upstream is thicker under the high speed of counter currents. So I am wondering why this is coming out under the higher speed of counter currents. The deposition of the upstream of the channel is thicker than the former, the lower.
Yeah, I know what you mean now.
Yeah.
Yeah, we were also wondering why this is, and because we had a lot of deposition inside the channel, and this is probably also something related to the conditions of the turbidite current, that it was mainly maybe a bit stopped by the contour current, and this could maybe generate more deposition inside the channel. So we are actually trying to think how to modify maybe the turbidite current so that we don't have so much deposition inside the channel, and we can better analyze a longer term evolution of the channel, because now we only did one event and almost the whole was filled in some occasions. And also we saw a reduction with the strongest current of the velocity of the turbidite current, and that might be also why we have more deposition inside the channel.
Okay, thank you. Well, you can see whether they are turbidite currents deposition or they are mixed contourites and turbidites. They may have different composition. That's my guess. You can see in the future experiments. Thank you.
Okay.
Thank you.
Elda, are you able to see the chat?
Yeah, I can open.
So in the last, there's 3 questions. One is from Xin Wang. Ask, do you have a PIV measurement to show the flow structure? That's you see the last 3?
Yeah. PIV meaning?
I don't know. So Xin, are you available? What's the PIV mean?
Hello.
Yeah, go ahead.
Something about turbulence,
PIV
maybe?
means, do you hear me?
Yeah.
Yes.
Yeah. PIV means particle image velocimetry. That can measure the flow structures.
I see. No, unfortunately, we don't have that. But it would be great. Maybe future investment.
Yeah, because I'm interested in the flow structures when the interaction occurred. I think if we can see the flow structures, maybe we can give more solid explanation about the interaction.
Okay, great idea. I'm gonna write it down for our future. Because actually, usually the turbidite currents that were being analyzed before, they only use punctual measurements in one direction, because they always supposed that it was just going downslope. And we already invested in this special one that measures in 3D. So this will be the next step then, even to improve it. Thank you.
So next question is 777. 777, you want to ask? You want me to? 777-33777. So Elda, you can read.
Yeah, I can read it.
Ask if the turbidite currents with erosion, how will the interaction between the 2 kind of currents, on the other word, if the channel without the levee, the migration of channel will match the film experiment?
Yeah. To answer that, we will need to do repeated experiments. So to have first one, modified bathymetry or topography of our tank, and then run another experiment on the top of it and see how this evolves with time. And hopefully we will see if it is migrating or not, and how this can affect the flow itself. But yeah, we couldn't do it at this point, also because of time constraint, but also because we had a bit of this problem of a lot of deposition inside the channel. So hopefully if we manage to create a experiment in which we have a more sustained development of the channel that is not going to die soon because it gets filled, maybe we could answer that.
So I'm being asked, do you have, what's your grain size mixture?
Yeah, we use a medium grain size of 133, I think. Let me check 1 second.
Hello, Elda.
Yeah, 133 medium grain size. And then a concentration of 15%. And we had in total a volume of 0.9 cubic meters.
Okay. Well, first, I'd like to say it was a great talk, very insightful.
Thank you.
But the reason I asked the question is that it seemed to me, I could be wrong, that the tank experiments would have less separation of grain sizes as compared to the bigger examples on seismic. Is that real or?
Well, of course, it doesn't fit perfectly because this is, as I say, mainly sandy deposits, and then we know that we use only silt. We didn't use clay, so we know that the effect of clay in the behavior of turbidite currents is very important. So of course, it's not going to be the case, but it has already been widely proven that this configuration represents quite well the formation of submarine channels. And that's why we also think that could also represent well this interaction with contour currents. So of course, it's not going to be exactly like in reality because it's impossible, but it's a good approximation because also clay makes everything more complicated.
But did you see a separation of grain sizes to some extent in your tanks, or?
We haven't measured that. But
okay.
that's something we have in mind to do in the future experiments, to try to take some samples and see if we also have a separation. This has been done for the turbidite currents experiments only, so there is some separation. So we will assume that maybe in this case, there could be even a stronger separation, but we will see. The problem is also that the finer sediments take some time to settle. So because the tank is not so big, maybe we have some recirculation of the deposits and that could be a bit tricky.
Yeah, okay. Well, I think the settling time would be a big component in that, because in the real world, of course, because if you have a cloud of really fine sediment that would settle very slowly, then that would be exposed to the bottom current for much longer than the coarser fraction. But
yeah, that's definitely okay. So I think I have a couple bunch of questions. Let me, very interesting. But let's, Elda, let's quickly answer the last question on the chat. It said, Pan Jun asked the difference across slope, bottom current, and turbidity currents.
The difference in terms of process, in terms of velocity, in terms of what? I don't understand very well. So bottom currents flowing along slope are related usually to the oceanic circulation, so the thermohaline circulation, and the turbidite currents are gravity-driven process with sediment in suspension. So the contour current usually doesn't bring much sediment in suspension compared to a turbidite current. So what's happening here is mainly we have water moving, and then this is pushing the turbidity current that is the one bringing sediment.
Okay, Elda, in your talk, one slide you show when you increase the contour current, suddenly you show the cross shelf, downstream is decreasing. Do you remember that one? You said you need. So here is a very important point. So could we establish an equation or a balance point when the contact current reach a certain level threshold, then the slope current or turbidity current begin to decrease. Of course, this may be related to the slope, the angle of the slope of the current or grain size, or of course the contact current velocity. There should be some balance. There should be some equation or curve.
Yeah.
To build.
So we need a lot of new experiments to start adding points to this future calibration curve.
Because I mean, because this is understandable, you know, when the contact current is small, it doesn't really affect the downslope, you know, discharge of movement. But when increase the contact current, and of course, this somehow is constrained, even a little bit depress the cross shelf current.
Yeah, and even more interestingly is when it's only a quick current, then the turbidity current flows faster than without.
So this we need that equation. We need to build up that, you know, should be some experiment curve show you know, the relationship with.
So I hope some experimental researchers here get inspired and maybe start doing some new experiments, and we can build together this curve.
And I think there's couple more interesting real world experiment site. One is the Ganges Brahmaputra, because the slope is big enough. There is a canyon go down, and that's a good one. Understand it's a cross shelf contact current and down slope.
We were supposed to be there this January, but
you know,
Corona was all. Hopefully in 2 years we get some measurements from that.
That's the one that's very interesting. Another one is the Nile River system. When the longshore drift go to the coast of Israel, after past the Gaza Strip, you know, when go to offshore of Tel Aviv, that's great place to.
That's an easier one to reach.
Yeah, I mean, well, if you look at Uri's talk, a couple talk, that's the place I want to work on with, because this is a combined longshore and cross shelf, and with the canyon, you know, developed turbidity current, maybe gravity current, and at least these two locations. I don't know about Congo, but this.
No, I think Congo is.
No, it's not.
It's too much.
Longshore. And
Run River, to be the current.
Run River, Ifemel's backyard, you know, Serge Benet and other people, they work on the Run River shelf, and also show that kind of go to the deep sea, but mainly longshore drift. But at least Ganges.
No, but there is also a current there, the northern current, that affects, so the whole water column is flowing also in this direction. And there is also the discussion about Coriolis or contour current, because it was argued also there was Coriolis.
Okay, there's more to talk about. Unfortunately, you know, we had to end it here. I have a class in 3 minutes. I had to leave. So, but it's keep in touch. It's very
definitely. Thank you very much.
Okay,
everybody, for the question, the discussion.
Very good. Okay, thank you, Elda. And so we had to end it here. Okay.
Okay.
Yeah.
Bye bye.
Bye bye.